Hey everybody, it's Mrs. Dr. B. We are dealing with basic gas laws. This video is about Gay-Lussac law. Every one of our basic gas laws, remember, begins with the ideal gas law, PIVNERT, which is up here in the upper left-hand corner. For Gay-Lussac, we are specifically talking about pressure and temperature. And so we need to understand that volume, moles of gas are both held constant. Easiest way to think about Gay-Lussac, it's something that we talk about or you guys do anytime you're on a trip or your parents are going to do on a trip, is you always inflate your tires before the trip with a cold tire most of the time. They tell you not to overinflate the tire because we understand that as the tires run on the road, they get hotter, and because they get hotter, the pressure increases. Anytime you're dealing with two things on opposite sides of the equal sign, it is a direct relationship. You can see this in your PTV stick. Since volume is not there, I'm going to hold on to it, and we can see what happens when I increase temperature, pressure goes up. When I decrease temperature, pressure goes down, which says it's a direct relationship. Up means up, down means down. Volume is not a part of the law. All right, so here is the simulation I've shown you pretty much for each one of the different labs, or laws, excuse me. You will see here that the gas source is not adding any additional moles of gas. You can tell that by the fact that the yellow container does not have additional have additional moles of gas or particles of gas. You can see that the pressure, I'm not adding anything for pressure. I'm not adding additional weights, but we can still see that the pressure is increasing. So this isn't because the volume decreases, it's because the temperature increases and because gases get hotter. When they get hotter, they hit the container more often, and that increases pressure. And you can see the direct relationship in the graph to the right. All right, so let's look at PVNRT, ideal gas law, and let's see how it converts over to Gay-Lussac's equation. We are getting rid of the volume, the moles of gas, and R, and it becomes our constant K. All right, so if you will turn your attention to the left, we're going to have P equals KT. In order to get K by itself, it's going to be P over T. Well, we always have a beginning one, and then we have an ending one. So then this becomes our workable equation for the Gay-Lussac law. All right. So let me go ahead, because there's really not a whole lot to this, let me go ahead and give you a couple practice problems. But this is one of my favorite stories to tell on Mr. Dr. B. He grew up in Kentucky. This is a true story, by the way. He got a new basketball because he lives in Louisville, and everybody loves basketball in Louisville, anywhere in Kentucky for that matter. So he got a new basketball, and so he went out one evening and he was shooting baskets in his backyard. And he just happened to leave his basketball outside. The next morning he went out to play. It was pretty cold, and the ball wouldn't bounce. Now, I'm not a basketball player, but he is, and I know that, you can't dribble a ball before you hit your free throw without, if it doesn't bounce. So he went inside disappointed, but he decided that, while he may not be able to dribble, he could at least take the cold off of the surface of the ball. So he put the ball in the sink, warmed up the water, and just ran the water all over his ball until the ball got hot. His mom wasn't happy because he ended up with water all over the floor. But guess what? Without knowing what he was doing, when he took the ball back outside, he expected it still not to be able to bounce, so he wasn't going to be able to dribble. But just by running hot water over the basketball, the ball bounced. So he discovered by himself the relationship between pressure and temperature. Totally by accident, but because he wanted to at least, while he couldn't dribble, at least be able to throw a basketball that wasn't ice cold. So I didn't give you the problem, so here it is, all right? So let's look at this practice problem. Notice it's all worked for you already on the screen, but I want to go ahead and work it so that you can see it happening. All right, so we have a basketball. It was filled with room temperature air. So T1 is 25 degrees Celsius. We're going to have to change that to Kelvin because all temperature has to be in Kelvin. P1 is 2.3 atmospheres. We can see that, and then it says down on the second paragraph, after leaving the ball outside, the ball didn't bounce anymore. I was asked, did it have a leak? But what he did is he noticed the temperature outside was 26 degrees Fahrenheit. 26 degrees Fahrenheit is below freezing. So T2 is negative 3.3 degrees Celsius. We're going to have to move that over to Kelvin also. So folks, we have P1, T1, and T2. What we are looking for is P2. Okay? So the solution is, in every one of these laws, if you're given this without being on a specific, is to look to see what's involved. Temperature and pressure is Gay-Lussac. No volume is not included. So what I want us to do first is let's change the temperature to K. We understand the relationship between Celsius and Kelvin. Negative 273 Celsius is equal to 0 Kelvin. That's going to be our conversion. So in order to go to Kelvin, we're going to take this 25 Celsius and add 273 to it. And what we're going to get there is 298 Kelvin. That's going to be our T1. Our T2 is the negative 3.3 plus 273, and that's going to give us 269.7 Kelvin. So instead of Celsius, we're going to use our two Kelvin values. Now all we have to do is put them in place. And we have 2.3 atmospheres P1 over 298 Kelvin. We're looking for P2, and we know we have 269.7 Kelvin for T2. So our job is just to work this problem. Again, I like to just multiply, divide, and then say it equals. All right? So what am I going to do? I'm going to take 267.9 Kelvin times 2.3 atmospheres, and then I'm going to divide it by 298 Kelvin to get my answer in atmospheres. All right, when I do that, these two guys multiplied, him divided, I'm going to get an answer of 2.08 atmospheres. So that's how this problem is going to work. We're going to use the P1 over T1 equals P2 over T2, and we're going to solve for whatever is left. Now hopefully this makes sense because the temperature decreased. If the temperature decreases, the pressure is going to decrease, and we can look at the pressure initially was 2.3 atmospheres. The pressure at the end was 2.08 atmospheres, and just the pressure made it so that the basketball did not have elastic collisions and it didn't bounce. All right, so let's go to the second problem. All right, the second problem is going to be using, again, the same material or the same formula. We got a P1 over T1, P2 over T2. Let's look to see what we've been given. We know that we have 9 liters of gas. It's found to exert. First thing somebody's going to want to do is they're going to want to use that liters. But what are we looking at? We're not looking at volume. This is a container that happens to be 9 liters. Don't let it fool you and make you think you got to use it. The only thing we're interested in using for Gay-Lussac is pressure and temperature. So let's find pressure. All right, we found P1. P1 is 83.0 kilopascals, just another unit for pressure. We have a temperature of 35.0 degrees Celsius. We know we're going to have to add 273 to that to get our Kelvin. And our Kelvin is going to end up being 308. This is going to be our T1 that we're going to use. Alright, so it asks then what temperature, T2, this is our question, but notice we're going to have to convert back to Celsius because it's asking for Celsius, would be required to change the pressure to standard pressure. So this provides us with a little bit of a challenge because you have to remember what standard pressure is. Remember, pressure can be in atmospheres, it can be in kilopascals, we could do it in millimeters of mercury, we could do it in a whole bunch of different ways of doing it, but kilopascal, I asked you to remember the number. The standard number for pressure for kilopascals is 101.325 kilopascals. So you may have to go back and get some notes from that, but that's what you're going to use for your P2. Alright, let's put everything in place. 83.0 kilopascals. We have a temperature of 308.0 Kelvin. We want the final pressure to be 101.325 kilopascals, and we don't know what T2 is. So the answer to this problem is going to be Kelvin, right? I'm going to multiply these two guys. I'm then going to divide by 83, and I'm going to set it equal to T2. Alright, so let's just do that. I got 101.325 kilopascals times 308 Kelvin divided by 83.0 kilopascals. Notice our kilopascals will cancel. Okay, they cancel, and I'm going to end up with Kelvin as my answer. My answer for this problem ends up being 375.9 Kelvin. But remember, we're asking for it in Celsius. So if we go from Celsius to Kelvin by adding 273, how are we going to go from Kelvin back to Celsius? We're going to subtract it. And when we subtract 273 from 375.9, we get 102.9 degrees Celsius, which is your answer for this problem. Alright, again, here you would expect the temperature to go up, because the only way to get the pressure to increase, which is what it did, it went from 35 all the way up to 101, the only way to get pressure to increase is by raising the temperature. Alright? So there's two practice problems. You'll get your assignment to, and you can use these to help you with that. Alright, so to summarize this, please remember all of our basic gas laws actually run off of the ideal gas law, PV equals nRT. In this particular case, Gay-Lussac is getting rid of the volume and the moles, so that turns into K. You see your workable formula on the right, and there's another example on the bottom. Alright, now there was supposed to be another slide. I don't know what I did with it. Gay-Lussac is a really hard gas law to remember. There's no real way to say it other than the fact that the man has a very weird name. So if you go with very weird name, you know that volume is not included. Sorry, there is absolutely nothing else I can offer you here, but that may be a way to help you. All right. So it is 15 minutes, 5 minutes more than I wanted, but thank you guys very much, and look for your assignment to follow. All right. Thanks. Bye.